Okay.
Oh, he'll do
Yeah.
for Zoom, but I mean, yeah, and you can.
Oh, we'll just
you can
pick.
interact with the audience
Yeah.
because my default would be not to ask for the students first.
Yeah.
It's recorded automatically, but I'll also record it here.
Why?
I think it is, but I'll record it.
And I'm not going to use the mic for my introduction.
Mitch, you'll turn down the lights, or should I do that?
The lights are already set.
They're already good? Okay.
I don't know.
Okay, cool.
Yeah,
I
it's
know
on
there's
the-
always like a thing.
You can change them if you want. Right, this is where we want the light, right?
Okay.
Yeah. Great. Okay. I can know all this stuff, but I can't use notes anymore.
You're being recorded.
Thank you.
Okay. Welcome to today's colloquium. Our speaker is a local.
Have you forgotten my name?
Yeah. I was about to. Anne-Marie Madigan, right?
Yes.
Yeah.
Yeah, you got it.
Anne-Marie got her PhD in 2012 at the University of Leiden. She went on to a NASA Einstein Fellowship at Berkeley, 2012 to 2016, and was concurrently a postdoctoral fellow at the Theoretical Astrophysics Center at Berkeley. And since 2016, she has been an assistant professor in APS and a fellow of JILA. Two other things I want to note is that Anne-Marie has gotten a number of distinctions, and since coming here, she has won a Packard Fellowship, and this year she is the winner of the American Astronomical Society Vera Rubin Early Career Prize. Is this the first time that that's offered? Or
No, it's a few years.
Just a few years. Okay.
Yeah.
Anne-Marie is a dynamicist. She studies the collective gravitational effects of small bodies in many different situations, ranging from the solar system to galaxies to clusters of stars around supermassive black holes. And it sounds from her title that we're going to hear something about most of those. She's going to tell us about collective gravity from icy planetesimals in our solar system to stars in orbit around supermassive black holes. Anne-Marie.
Thank you very much, Mitch. You don't have to clap at every slide, but I appreciate it. Okay, so as Mitch said, and thank you for the kind introduction, I'm a dynamicist. So I study dynamical problems on many different scales. And on Friday, I thought I would give you a talk that spans icy planetesimals in the solar system. You see where the subtitle is coming from, all the way to clusters of stars and galactic nuclei. And the surprise is I can't fit that much in one talk. So you're getting planetesimals today. But at first I want to give you a brief background. Mitch said a lot, but I want to basically tell you. So I was born in Dublin in Ireland, and I went to school when I was 4 years old. I was very shy and very nerdy, but very, very excited. And when I was 16, I took my first ever physics class, and the teacher wrote on the board at the question, "What is light?" And from then on, I've just been hooked on the idea of studying physics, and so I feel really lucky that I still get to do this as my job. I moved to Galway to study physics and astronomy because the best thing about physics is astrophysics, and Galway is the only place in Ireland at the time that you could do that from undergrad. So from there, I decided to go to Leiden University in the Netherlands to do cosmology. But I'm standing here today as a not cosmologist, and the reason for that is that I took general relativity with a professor there called Yuri Levin, and I also heard a talk by a postdoc, Clovis Hopman, all about the orbits of stellar mass black holes in orbit around supermassive black holes. And so the best thing about astrophysics is, of course, black holes, and so that's what I did for my PhD. Everything around black holes. I then had enough of rain, and I decided for a postdoc that I wanted to move to the US. And so I took a postdoc position at UC Berkeley, where I got interested in magnetized gas dynamics, particularly in galactic centers. And also I became interested in our outer solar system for reasons I hope you'll get on board with for the rest of this talk. Of course, the end of the story to this date is that I moved to Boulder in 2016 as an assistant professor. So just want to say briefly what I do now here in Boulder before I get on to my research. I'm of course an outdoor person because I live in Boulder, and my latest hobby is the one I made up that I mentioned a few weeks ago. I call it CrossFit. It was due to an excellent suggestion, I think, by one of the grad students in the chat window. This is where I cycle long distance, or sometimes just down the road, and I sample croissants. Sometimes I bring a paper with me, one of my students' papers, to read, and it's just all around a glorious, glorious time. My other hobbies include hanging around with this little one who's already 2.5 years old. For everybody who remembers, she was born like a month ago. So our hobbies together involve a lot of playgrounds with a certain other professor I'm not staring at right now, and talking a lot about owls at 6 a.m. in the morning, including this morning. Okay, but on to the astronomy I'm doing in Boulder. So I'm going to touch on the 3 major research areas that we focus on in my group, and you'll see alongside my group members, yellow for current group members and gray for former group members who have been working on these projects and leading the projects in my group. So on the largest scale, we have the dynamics of dark matter in barred disk galaxies. So bars are these fantastic elongated features that are made up of aligned stellar orbits. So the stars moving on their orbits, and they're all clustered together. So that's why you get this elongated brightness feature at the center of these galaxies. They're very common. So what Angela has been leading is a project showing that dark matter, depending on its orientation in the dark matter halo, can fall into that elongated bar and form a shadow or a parallel dark matter bar. But also, if the dark matter is actually moving against that direction of the bar motion, you get awake.
It seems that you are not coming through on the Zoom. I've got a bunch of people in the chat. Let me unmute myself. Can we arrange? I think you're unmuted, but you...
Okay.
Can you keep talking?
Sorry, yes. Can you hear me on Zoom? Dark matter. Dark matter.
Nick Schneider is shaking his head.
Oh, dark matter. I'm not sure what to do. I am unmuted here.
On the mic, are there different options if you go to the pull down?
Same as system.
Yeah, try some of those options.
Okay, we're going to try some of these options. So dark matter is...
Can people hear me? Oh, Nick's got his thumbs up. So you're hearing, Nick. Re-speak.
Dark matter. Planets.
Nick, did you hear that? Okay, I'm getting positives now.
Yes? Okay. I'm sorry to everybody on Zoom. You didn't miss much. It was the best part. Croissants and daughter. It's all downhill from here. Okay, let's move on. Dark matter, super cool, novel spaces to look for annihilation signals. And now this is broken. Okay, but the main research area in my group is actually on a smaller scale, and that's the dynamics of stars in stellar clusters. It's not working.
Can you stay closer to the microphone and not move around so much?
Okay, so it's this.
Zoom.
Okay. Okay.
Sorry.
No problem. Okay. So what I'm showing you here is, it's going to be really hard not to move around. I'm just going to go like this. What I'm showing you here is a beautiful Spitzer image of the M31 galaxy. That's our nearest neighbor, Andromeda. And zooming into the center, we have this mysterious double nucleus. And so you would think from looking at this is that maybe there's 2 star clusters in orbit around a supermassive black hole, but that's not what's happening. And I will tell you at the end of this colloquium what is happening, because it relates to what we're doing in planetary dynamics. But this is a system that we work on trying to understand how it formed. In particular, Tetsuya is working on this. How is it stable? And then how are stars interacting with the black hole because of the system? We are also really into our own galactic center. This is a movie taken of from data over 25 years of the stars moving around a black hole at the center of our galaxy, for which Andrea Ghez and Werner Genzel won the Nobel Prize last year. And so we're really interested in the origin of these stars around the black hole and also how they relate to stars that are escaping the galaxy in the galactic halo. And that's a project being led by Alexei. And then lastly here, Maria and Karen have been looking at the rotational globular clusters as they move in the tidal potential of the galaxy and why they're not tidally locking. Okay, and then finally, I really want to pace. I'll just kind of go here. So finally, in my group, we've been working on planetary dynamics. Okay? And so this is really being led by Alex Zederek, who will be defending his thesis next month. But a lot of other people have jumped in on this project and bringing their expertise from galaxies and star clusters and trying to understand what's going on in particular in our outer solar system. And so this is really the theme of the talk, right? This collective gravity. And what we're showing is that if you take minor planets, and these are asteroids, or comets, or dwarf planets, anything smaller than a planet is what I'm going to put into this category, and you move them far enough away from the giant planets in our solar system, and not so far out that passing stars are going to grip them and take them away, they are relatively isolated and will start gravitationally interacting with each other and can produce really interesting structures like the one you see here from a press release last year. So we're going to be talking about orbital dynamics. How does that actually work and how it can explain things, mysteries going on in the outer solar system. So let's talk about orbits. Okay, it's going to be just a 2D orbit to begin with. Here we have a major axis of an orbit, and the quantity you'll see throughout the talk is the semi-major axis, half of the major axis. Okay, so that tells you the size of an orbit. The minor axis, given here, really tells you something about the shape of the orbit. If that minor axis is large, you're going to get something more circular relative to the semi-major axis. If it's small, you get something more eccentric. And this here is the semi-minor axis. So eccentricity is just relates that semi-minor axis to the semi-major axis. Okay, so if your semi-minor axis is very small relative to the semi-major axis, you're going to get this cancelling to 0, and you get an eccentricity of 1, and vice versa for an eccentric orbit, or for a circular orbit. Two other distances, or points along the orbit that you'll hear about, is aphelion. So this is the position here furthest away from the central body on an ellipse, and that's the sun in our case. And then we have perihelion. Sometimes I'll say pericenter, apocenter, because we use them in stellar dynamics too. But the perihelion is given by semi-major axis times 1 minus eccentricity. So for the same semi-major axis A, if you have a circular orbit, your perihelion is relatively large. It's just the same as the semi-major axis. But if you get a really eccentric orbit and that eccentricity drops to 1, or close to 1, your perihelion gets really, really small. And so we'll be discussing perihelion in this talk and how orbits of minor planets can gravitationally torque each other and change each other's eccentricity, and really affects how they interact with the inner solar system because it changes their perihelion distance. Okay, that's 2D. Moving quickly on to 3D. So how do we describe the orientation of an orbit in space? Stellar dynamicists do this right and use vectors, and we use angular momentum vector that points normal out of the orbital plane, and eccentricity vector tells you where is your perihelion located in space. Solar system dynamicists, it's probably good that I don't know who's on Zoom, they use Kepler elements, no judgment. So Kepler elements give you angles that the orbit makes relative to some reference direction and reference plane. It can be a little non-intuitive then to understand how your orbit will move if you torque it or things like that. But I'll talk you through it because we're going to be using the Kepler elements. I'm going to use the analogy of a boat. You can also use a plane if you would like it. But I want you to imagine you have a rope around the edge of this boat, and that's your orbit. And so the rotations that you have to play with as an orbit are the same as the rotations for a boat or a plane. Okay? So you have your pitching forward and backward over your minor axis. You have your rolling left to right over your major axis. And you have a yaw, or redirecting your eccentricity vector or your perihelion direction. Okay? How does that relate to your Kepler elements? Inclination, and this is just going to be qualitative here. Inclination is pretty intuitive. It's just like, what is the total amount you're rolling or pitching? I don't know which direction I'm doing that in, but what is that total amount? Argument of perihelion, omega, you're only going to see omega because I don't want to write argument of perihelion throughout the talk, is, at least for low inclinations, how much am I pitching by how much I'm rolling? And I will repeat this again if we use it. You don't have to memorize this. But you can imagine if a group of orbits are all facing in different directions, but they all have the same omega value, this is really odd. It means no matter where you're facing, you're all, for example, pitching forward and rolling to the right. Why would the outer solar system be doing this? It's kind of a hint to tell you the outer solar system is doing this. And then finally, we have an element. It could be omega bar. Var pi is what you use when you write it in LaTeX. For some reason, my group calls it pomega, and I'm not sure where we got that from. I might blame Eugene Chang in UC Berkeley, so it's pomega for this talk. But it's basically yaw. Which way are you facing? Which way are you directed? Okay, so 3 more slides on just how you actually change an orbit. And then we'll get on to what's going on in the outer solar system. So the first and one of the most important ways to change your orbit is gravitational scattering. Okay? So you have this blue body moving around the sun on an orbit, and let's say in your perihelion, it comes close to another body, and it gets gravitationally scattered. It feels the gravitational acceleration, and it moves it onto another orbit. So this is highly exaggerated here. What's key, though, is that although it moves onto another orbit, it's just a perturbation. So it's still on a Keplerian ellipse, and it meets back where it received that perturbation. It's just changed its shape and its size. The key physics underlying all this talk is gravitational torquing. And so the idea behind this is, let's say you have a planetary system and you have no massive perturbers in the system. You have no strong scattering events at all. You have these just individually low mass bodies, and you set it up so they never actually come close to each other whatsoever. Are their shapes, are the orbits themselves ever going to change? And the answer is yes, because these bodies are going to be repeating the same orbit again and again over really long time scales. And so you can imagine having their mass spread out along their orbit, and then you have a system of massive ellipses that are gravitationally interacting with one another. And this is called torquing. It's the rate of change of angular momentum, torque, and it changes the shape of the orbits. And it can be really, really fast, much faster than any type of scattering encounters. Okay, lastly, we have precession. So, for example, if we have an outer solar system body that never comes near the giant planets, it's still going to feel the effects of the giant planets through precession. So if this body was only in orbit around the sun, it would never change its orbit. It would always come back and land exactly where it started forever. But because of the effects of those giant planets, even if they're really far away, your orbit starts to not perfectly close. It starts to open out. And everything in the universe makes you open out a little bit. And I've shown a highly exaggerated version here. So this is going to be really important when we look at simulations of bodies in the very outer solar system, very much isolated from the giant planets. They're still going to feel this apsidal precession effect. Okay, good. On to my talk, now that we've got the basics over with. So something really odd is happening in the outer solar system. So I'm going to explain some of the observations. I'm going to introduce something called Planet 9, and I'm going to take it away and show you don't need it. So first, a schematic of what am I talking about when I talk about the outer solar system. So I've got semi-major axis on the x-axis in AU and on a log scale. And I've got eccentricity going from 0 to 1. So you can see here we've got Earth, we've got the gas and ice giants that are on the horizontal axis because they're in roughly circular orbits. And then we have Pluto with a significant eccentricity. Pluto is part of an icy distribution of leftover planetesimals from the formation of the solar system, known as the Kuiper belt. And then it spans from about 30 to 50 AU. And it's like the asteroid belt, but it's icier and more massive. Arching out of the scattered disk population, or the Kuiper belt population, is the scattered disk. So the scattered disk objects are quite like the Kuiper belt objects, but they show this structure in semi-major axis and eccentricity space. And what this is that no matter where they are in the outer solar system, their pericenters are all roughly at 30 AU. And the reason for this is that they're currently scattering or have the potential to scatter off Neptune, which is at 30 AU. So they come close to Neptune near perihelion. They may have a gravitational encounter that puts it onto a different orbit, but it's still on an ellipse, and even if the shape and the size of the orbit changes, for example, moving outwards and getting more eccentric, we'll still come back to that position. So their perihelion position is conserved under the scattering process. So we see this lovely scatter disk in AE space. So everything here we understand. I'm just going to pretend we understand the Oort cloud. One thing I can say is to get out to the Oort cloud, you can move through the scattered disk till you get so far out in semi-major axis space that it's easy for galactic tides and passing stars to actually change your orbit. You can get stuck out there. What we do not understand yet are a population of objects called detached objects. So these are bodies in the same region of semi-major axis space as the scattered disk population, but they have lower eccentricities. And what that means for their perihelion distance is that their perihelia are nowhere near the inner solar system. They do not come close to Neptune. So they are not scattering from Neptune. And so this is a mystery. We don't think they formed out there. The original protoplanetary disk would have been too low mass to form these objects. They had to have traveled out there, but we do not understand how they did that given the orbits we see them on right now. So that was a schematic in AE space, just to show you this, like the size, the real scale of these orbits. Damn it. Hello. So to show you the size and the scale of these orbits, thank you, Andrew. I'm showing here the inner solar system. We have the asteroid belt here and Jupiter's orbit in orange. Moving outwards, we have the outer solar system. You'll see the Kuiper belt in blue and Neptune there in blue. Also blue, Pluto in purple. I don't know why I'm telling you all the colors. And then we see Sedna, right? So Sedna is one of these detached bodies discovered near perihelion. And if you think it belongs to our solar system, you might imagine, okay, its orbit is bigger, but it's probably going to look pretty similar. But this is Sedna's orbit. So it's extremely large. It takes over 10,000 years for Sedna to complete one orbit, and it's extremely elongated. But you'll see in this inset, even at its closest approach, a perihelion, it is nowhere near Neptune. So it never has a strong gravitational encounter with any bodies in the inner solar system. So how did it get there is really the key. And now we want to take a whole bunch of these detached objects and put them together. What do they look like in that case? So this is a plot from a Nature paper in 2014 that really sparked a lot of the more recent work in the outer solar system. And we've got semi-major axis on the x-axis, and we've got this argument of perihelion on the y-axis. So this is the omega. This is like how is your orbit tilted with respect to the plane of the solar system. And so what you see is beyond about 150 AU, these bodies are not just uniformly randomly scattered throughout this tilting space. And in particular, they're clustered. They have values of, on average, about minus 20 degrees. And so what does that look like? I'm not even sure if this is exactly minus 20 degrees in omega, but this is the type of geometric picture you should have in your head. And it's odd. This is not something any other population in the solar system is doing that we know of. Just going to point out we have Sedna here in red, and we also have one of my favorites, 2012 VP113. I thought somebody would be like, woo! But okay, cool. That's fine. This object has a perihelion position of 80 AU, or perihelion distance, so it is not at all close to the inner solar system at any point on its orbit, and its nickname is Biden, because Biden was VP in 2012, which I love. Okay, I'm just going to summarize the rest of the mysteries going on out there. I don't want to show you absolutely every single plot. So number one, we have the detached objects with perihelia much greater than 40 AU that really demand an explanation. And they're really hard to see, I should say. So these bodies, we only see them because the sun is sending light, hitting off their surfaces and coming backwards. So it's a 1/r² penalty. It's really, really hard to see detached objects that have perihelion that's really far out in the outer solar system. So if we see one or two, there are more in your aphelion. We just can't see them. They have also really high inclinations. I'm just going to mention one that was recently discovered is nicknamed Cashew, and it has an inclination of 54 degrees with respect to the midplane. So again, this is another strange orbital configuration that needs an explanation, and it doesn't fit in with our idea of solar system dynamical evolution. I've explained clustering in omega, and finally we have clustering in pomega, or physical space. And you'll see what that looks like on the next slide. But taken together, these mysteries have really motivated what's called the Planet 9 hypothesis, in that something is forcing these orbits of these minor planets into this strange orbital configuration. And so this here is what orbits look like when they're clustered together. The purple orbits in particular, we have Sedna, we have Biden, which is still my favorite, despite the strange response. And here, this is from the press release in 2016. Here is the Planet 9. Yes, I'll put this up. The latest 2021 updates for what this planet needs to be to explain the outer solar system data is it needs to be a super Earth, sub-Neptune, kind of around 6 Earth masses. It needs to have a semi-major axis of hundreds of AU, and high eccentricity, about 0.25, so very different than any of the planets we have in our solar system that we know of today, and a high inclination orbit of around 20 degrees. And so in numerical simulations, if you put that type of planet into the outer solar system and you sprinkle test particles in its area, you will see that Planet 9 really beautifully gravitationally torques orbits away from it into this configuration. It also induces high inclinations, it can detach bodies, it can do everything that we see in the outer solar system. Okay, but obviously I'm here to tell you that they're all wrong. So maybe, yes, maybe I should say, so people are really searching for Planet 9, which has been really exciting because they keep capturing in their telescopes new bodies that can either add or take away from the signals we think we're trying to explain. And so it's a very intensive and very exciting search. But in our group, we've been working on this theory that it's the collective gravity of these minor planets that are doing all of these things themselves. Much like when you look at a galaxy and you see spiral arms or a bar, you don't hypothesize a new massive supermassive black hole, for example, in the halo that's doing this. You say you have billions of stars to work with. They are making these structures. So that's the idea behind this. So what I'm going to show you next are simulations where we've included what we call a primordial scattered disk. So this is much like the scattered disk we see in our solar system, but we make it way more massive. And our motivation for that is that early in the evolution of the solar system, when we think the giant planets and the ice planets were moving around, they would be scattering a lot of mass into the outer solar system and away into the Oort cloud. And if at any point that scattering population from about 100 to 1,000 AU reached about 20 Earth masses, it's a lot, but there was more mass than that originally, then you're going to see what happens. Okay, so we put that population in, a massive primordial scatter disk. We also include the orbit average influence of the giant planets, which turns out to be really important because the giant planets induce this precession effect of the bodies in the outer solar system that weakens torques between them. So we need to include that. And of course we have the sun. And so this is the type of top-down configuration you should think of. So this is the evolution of a massive scattered disk. On the left-hand side, I'm showing you an edge-on view of this system. And so there's a surface density, edge-on, going from purple, the least density, to yellow, the most dense regions of the system. And then on the right-hand side, you're going to see a face-down view, and I'll play them one at a time. The axes here show till about 500 AU. We do simulate till about 1,000 AU, but the particle number gets really low out there, so you can't actually see anything in these plots. The last thing I'll note is that you're going to see timescale here in units of the secular timescale. That means long-term or orbit averaged. But for the purpose of this talk, you can think it's about 2 million years. And the simulation is going to run up till about 800 million years. So let me get started on the left-hand side. And I just want to set this up. If this was a disk of circular orbits, you would expect the disk to just get puffier And so edge on, it would just get a little bigger, a little less dense, just due to two-body scattering or scattering encounters. So this is what happens in your primordial scatter disk. So what you see here is that all of the orbits, just through their gravitational torques, made them incline exponentially fast off the midplane. You'll notice it actually has an X shape that's quite reminiscent of buckling of galactic bars, if anybody has been interested in that. And so let's look at the right-hand side in surface density plots. I'll set this moving. It might look like the extent of the disk seems to decrease, and what you're seeing there is that the orbital eccentricities decrease. So as you incline off the plane, your orbital eccentricities have to decrease. You have to get more circular to conserve angular momentum, and it's just through those inter-orbit torques again. And what that means is the population detaches itself from the inner solar system, even though it started off in a scattered disk. Okay, so I'll play them together at the same time. And I will try. Nope. I will try play them together. Perfect. And so what you're seeing here edge on is something that we call the inclination instability. So basically the inclinations of all the orbits in the disk, it's a global phenomenon, start inclining exponentially with some e-folding timescale off the midplane. And the inclinations never recover. They always stay median, extremely high values, something on the order of 60 degrees. And on the right-hand side, what I want you to notice is that peak density is lopsided. And now right now, it's pretty faint, so I want to show you some quantitative measurements of what you're seeing there. This is orbital clustering. So relating it to the Kepler elements. That inclining off the plane is clustering in omega, remembering that this is the kind of geometric interpretation of what happens when all of your orbits have the same omega values. And then on the right-hand side, we have clustering in physical space, or in omega. You can think of it schematically like this. You've got lots of orbits, but instead of being randomly distributed axisymmetrically around the disk, there is some alignment and kind of covers this feature like this. Okay, so we produce high inclinations. We detached all the bodies. They cluster in omega over really long timescales, and they also cluster in omega. To give you some quantitative data for just movies, what I'm showing you here are the results of very recent simulations where we have binned the particles or the minor planets in our simulation according to semi-major axis. So that's the color code in the top bar. So the first plot I'm showing is the mean of each bin in their inclinations over a long time scale, so like 800 million years. And what you'll see is that exponential growth as the orbits all incline off the plane, and they never recover. So this is the mean. There's a large dispersion, but it remains a very high inclination population and never comes back to the midplane. You'll notice that the innermost bin of about 100 to 200 AU tries to undergo this inclination instability and kind of collapses, and that's because of the effects of the giant planets. It would, without the giant planets being there, be the most inclined population at the end. But because of that procession, moving orbits around, the torques get broken, and they can't take part in the inclination as much. Here I'm showing the mean eccentricity. And so you start off with really high values, and you can end up with values of like 0.4 eccentricity. And that means that the perihelion distances of all these bodies are really, really pushed back. So now they're not interacting with the inner solar system anymore, and they're isolated. They're not near enough to passing stars or galactic tides for their orbits to be changed, but they're no longer in contact with Neptune, so they're going to stop scattering. These plots, I'm not going to explain exactly what EZ and ER are, but this plot here is a signature of omega clustering. You can think of it as the orbits pointing up or down off the plane. So in the first example, all of the orbits are pointing down here. They rise up again, they go down again. And so that's omega clustering, and it lasts for the entire simulation. And then ER is just strength of omega clustering. And so the noise floor, 1 sigma and 2 sigma, are these gray bands. And so if any of these bins rise above the noise floor, you've got clustering of orbits together. And so you'll see we get this in our simulation. It's a robust result, but it's very noisy. It looks like it rises, it drops down below the noise floor, and it comes back up again. So what we want to ask and answer is this actually real? And why? This is a relatively recent result. Alex, hello, ran into my office last year to tell me about it. We'd never seen it before in our simulations. So we want to know, like, is this just wishful thinking? And then if it is real, why? Well, what are they doing, these orbits? And so what I'm plotting here on the y-axis is a measure of the strength or persistence of this omega clustering, so that's the orbital clustering in physical space, as a function of the number of particles in our simulation. Yes, we have very few particles in our simulations. These are extremely high accuracy codes that are amazing and amazingly slow. But we do what we can. Okay, so what we're showing here is that as you increase the number of particles in your simulation, and we get up to about 1,000 now, we're keeping everything else the same, including all the collective mass of those minor planets. So individually, those minor planets will have less mass as you move outwards here, as you go to 400. And the reason the persistence and the strength of the clustering increases is because you're going to have less violent, less strong gravitational encounters between the particles, because they're individually of lower mass. Your potential is smoother. And what that means is that particles moving on these orbits will not be shoved around quite so much, moved onto other orbits. And this is really what would happen, right? We have billions of real particles in our solar system. We shouldn't be simulating 100 or 400. And so this tells us that as we increase the number of particles in our simulation, we should see this clustering effect get stronger and stronger. But of course, we want to understand why it happens. And to do that, we need to know two particular things. So I've already mentioned that orbits of low-mass bodies, and even if they never come close to each other physically, they exert long-term gravitational torques on each other's orbits. And so we'll use these two equations here to understand what that does to the orbits. So angular momentum, J, or specific angular momentum, is given by r cross v anywhere on the orbit. So you just go to the aphelion of your orbit and say r cross v, and you know where your angular momentum vector is. The torque induced on an orbit is given by r cross f, where f is the gravitational force. So if your gravitational force is in roughly the same direction as your velocity, you can say, okay, my torque is positive, I'm going to increase my angular momentum. I'll go through that again in the next slide. How this relates to the shape of your orbit: if you have more angular momentum J, your orbit is more circular, or your eccentricity goes down. So that's going to be important. Now, the second thing to understand is that normally circular orbits precess faster than eccentric orbits. And the way to understand this, so that's the speed of precession, how fast you open out, is a function of eccentricity. So an undergrad in my group, Jacob, actually came up with this analogy. It's all about boats. Picture a kayak. If you have a really, really long eccentric kayak, it's going to be really hard for you to reorient or to precess. But if you have a really small circular kayak, it's going to be really easy. So that's the way to understand it. And I'm using the word normally here on purpose. I'll explain that in a moment. So taking those two things, that orbits exert gravitational torques on each other, and the more circular you are, the faster you'll precess, we can explain why we get orbital clustering. So let's imagine we have our system of massive or minor planets in the outer solar system in orbit around the sun, and a few of them, just through numerical noise, happen to overline with each other. So this is what I'm showing here in this kind of thick blue line. They're going to be moving counterclockwise in their orbit, and they precess retrograde. They precess in the opposite direction, meaning the orbit will open out in the opposite direction. We can ask, what does this random overdensity cluster of orbits do to a nearby nearby minor planet orbit? So we write down our equations. We say this thinner orbit has an angular momentum pointing out of the plane, because it's r radius vector cross v, gives you angular momentum out of the board. But the torque it feels, let's just say at aphelion, where most of the mass of the orbit is located. It spends most time near aphelion. That force is directed in the same direction roughly as the velocity vector. So that means, if you just look at the equations, that the angular momentum change is going to be positive. Torque acts in the same direction as angular momentum vector. If your torque is positive, your angular momentum increases, your eccentricity decreases, you're a small little kayak, and you process faster. So this orbit is going to get more circular due to that gravitational torque, and it's going to speed up in precession and move away from that overdensity. So normally, you torque each other's orbits such that you actually spread out from each other. You would not expect clustering. So the reason I used normal is because you can wonder, are there going to be some regions, some gravitational potentials, where eccentric orbits process faster than circular orbits? Because then you're going to have torques that actually pull the orbits together. Yeah, as I said here, in these abnormal regions, the orbits will torque and they'll want to actually cluster together in the plane. So what we did is we looked at our simulations, and here I'm plotting now eccentricity on the x-axis and semi-major axis on the y-axis. And these black points are the initial conditions, and they're in a very small area of phase space because they're all part of a scatter disk population. There's a relation between their semi-major axis and their eccentricity. And you'll see the underlying color code is a normal region and then an abnormal region in orange. And you could think like, okay, well, if we let the simulation run, we know that these minor planets are actually going to drop in their eccentricities, so maybe they'll go into the abnormal region and then can start clustering. But what happens also is the abnormal region rushes up to meet them. And the reason for that is you've started off with a disk-like orientation, and then you've produced a cone. It's really odd gravitational potential, and that different gravitational potential has a much larger abnormal region. And so in this orange region, orbits torque each other and move towards each other, and then they're more gravitationally able to torque more orbits and shove more orbits together. And this is why you would actually expect orbital alignment in the outer solar system. Why did I use abnormal and normal? Because this, what I've just described to you, is Lynden-Bell's bar-forming mechanism. So in 1979, Lynden-Bell showed, using roughly this type of analogies with orbits and torques, that areas in galaxies, he looked at an isochrone potential, have these abnormal regions, particularly the areas in the centers of galaxies. And so you get these orbits that torque each other and want to align and get stronger and stronger and stronger. So what we're using is actually Lynden-Bell's bar-forming mechanism in the solar system, and showing it should act in exactly the same way. But you need that inclination instability to grow that abnormal region. It doesn't exist otherwise. One thing I want to say before I get to my conclusions is that to bring up that M31 strange double nucleus again, that looks like it might be two star clusters, what it is in fact is a system of aligned stellar orbits around a supermassive black hole. So it seems like in star systems, the scale of galaxies, and also in their nuclei, you get alignment of stellar orbits everywhere. It's a very common feature. And what we're proposing is that the same dynamics will be at work in a planetary system, but the reason this hasn't been as obvious before is that asteroids and comets, these minor planets, don't shine like stars, so we haven't been able to see those systems. So I'll be summarizing in the next couple of slides just to say that we can actually explain everything going on in the outer solar system, including the detachment of bodies. They do that themselves. The very high inclinations, clustering in omega, the tilts, that's because of this instability, clustering in physical space due to Lynden-Bell's mechanism. I'm just going to say perihelion gap for anybody who's interested, but I'm not going to describe it. It takes way too long. But we also explain something else that the Planet 9 theory has a hard time explaining. And it's all due to minor planets self-organizing under their collective gravity. Now, we don't get this for free. We don't just get to have 12 minor planets in the outer solar system do this. We need a lot of mass in this primordial scatter disk population. And so the number we're arriving at is uncomfortably large. It's by 20 Earth masses. There was a lot more than that in the planetesimal disk left over after planet formation, but it's still an uncomfortably large number. So that's really the Achilles heel. But it does make a very strong prediction, which is really nice. We don't know how much of that mass will still be left. We can get into like the mass flux coming back into the solar system. But let's say it's 10 Earth masses as a good roundabout figure. So our prediction is that there will be a new, we call it Kuiper belt in the outer solar system, but it would look very different than our Kuiper belt. We predict it's lopsided, it's extremely high inclination, but it does mean that we don't need a Planet 9. And so we're really excited to see what the observations say in the next few years. It will be a new massive source of high inclination comets, and there's evidence that we actually need this in our solar system. So Halley-type comets are comets with a broad distribution of inclinations, in a short period, about 200 years or less. And so it's thought that they're originating from the Oort cloud, then we can't actually explain their inclination distribution. They don't appear to be coming from a spherically symmetric source. Indeed, their median or their mean inclination of these Halley-type comets is 55 degrees. And just checking my plots this morning, I found that our high inclination objects at the end of our simulations have a mean value of 55 degrees. I was like, yes. Yes. Okay. And finally, for future work, we're working with the LSST team at the Vera-Rubin Observatory with their survey simulator to see what constraints Vera-Rubin Observatory will be able to place on this, this new structure in the outer solar system, if it's there. We're also very interested in thinking about in many more stellar occultations that should be happening at high inclinations, not just near the ecliptic, and also presence of extra dust, high inclination dust in the outer solar system from interactions of these minor planets. And then lastly, this may not have happened in our solar system, right? If we never had enough mass in that scattered disk region, maybe there really is a Planet 9, and that's what we need to explain the outer solar system. But this will have happened in other planetary systems, particularly ones that have giant planets and a remnant planetesimal disk that gets scattered. So we're excited. We've been working with Meredith McGregor, thinking of that exoplanet debris disks, and in particular debris disks with wing-like morphologies, and seeing if we can explain those features. So I will wrap up now, and I just want to say a huge thank you to all of my group members, from undergrads, graduate students, and postdocs. You've really been a joy to work with. So thank you so much. I will take questions.
Repeat the questions.
Okay.
From the audience.
So we'll start off with grad students, or any students.
You can tell people they can put something in the chat.
And you can write in the chat window. Andrew Hamilton is monitoring. Yes?
Oh, are there any?
There are no student
so
questions.
what would it take to get Madigan and Brown to give up?
I don't know. I think they have a new paper out, and I think they would have to be very unlucky with the properties of Planet 9 for Vera-Rubin Observatory not to be able to detect it. So it won't completely, if they don't detect it, it won't completely rule out that it's just an extraordinarily low albedo object. But it would definitely make it harder to believe if Vera-Rubin doesn't see it.
I have a related question, which is, are these two hypotheses really mutually exclusive? Could you have both Planet 9 and also this population?
Yeah, so I forgot to repeat the question before, but yeah, so the question is, are the hypotheses mutually exclusive? And they're not, and so I keep thinking of minor planets in my scenario, but there's no reason you couldn't throw in a planet, kick in an Earth mass. The only thing I would say though is, you don't need both. Right, so it would be strange to have something. I mean, Planet 9 used to be more like 10 Earth masses. Now that it's down to 5, it's a little more comfortable. But you certainly don't need both to explain the dynamics. And so I wouldn't hypothesize both.
Can I follow up on that, because I have a similar question? But you say you don't need both to be present, but the effects that you're talking about, the dynamics, should always be there, right?
Yes, yeah.
So So it's more, I wouldn't, I'm not sure if I understand when you say you don't need both. I mean, you will have Planet 9 and everything you just talked about is still there, right?
Oh, thank you for the question, actually, yeah, because I should clarify what I was thinking there. So the question, I'm not sure if I can repeat the question perfectly, but the question is, or maybe I will just take it and say I would like to clarify what I said last time about Planet 9 plus a massive disk. If there is a very massive Planet 9, yeah, you can have both. I'm sorry. Yeah, I was like, oh, you won't undergo the instability and things like that. But no, you absolutely could. So you definitely could have both. Yeah, there is no reason that they're mutually exclusive. And I just think about taking one of those minor planets and pumping up its mass. And all the dynamics will still work. You know, the more massive planet will introduce some other effects, I'm sure, than just, you know, everything is exactly the same low mass. I don't think you need both. If you've got the massive disk, you know, maybe one is more massive than the other, but you don't need a separate Planet 9 theory. I see a student question.
I tend to think of stars and galaxies as like a pretty long-lasting structure. Would you see this behavior for like a long time in the solar system, or would it eventually evolve into something else?
Yeah, thanks. So the question was stars and Andrew? There's an echo.
Sorry.
So the question is that bars and galaxies are very long-lived features, and so would you expect a lopsided structure in the outer solar system to be long-lived too? I would, and something I didn't get into is that in a very different approach to dynamics, there's a group at Columbia, including Year 11, who've been working on statistical thermodynamics of star clusters around supermassive black holes, and finding if you have a rotating star system around a black hole, there is a lopsided equilibrium that it will want to go through these orbital torques that are acting in between the stars. Sorry, I've said this kind of clumsily, but that's the same system as we have in the solar system. We have a rotating system of small bodies in orbit around a massive body. And so the statistical equilibrium for that system appears to be lopsided. So it seems like this is actually an equilibrium configuration for a planet system too. But you know, as long as you get away from massive perturbers like Jupiter, for example, that introduce all these precession motions that prevent inter-orbit torques from being effective.
I have a question in the chat for you. It says, when you showed plots of model output versus time for different populations, mean inclination and mean eccentricity seem to reach a steady state equilibrium. However, ER and EZ did not. Why is that?
Okay, so the question is, and maybe I can go back very quickly, is when I showed these plots, let me just open up all of them. You can see that the Kepler elements, inclination and eccentricity, seem to plateau and reach a plateaued value. These are their mean values, but why not EZ and ER, these measurements of clustering? And okay, so if we start off with the omega clustering, this is due to planets all inclining and pitching in the same way and rolling in the same way. And that first dip you see is because the noses of the orbits are all pointed downwards. And then they point upwards. What's happening there? It's that they're precessing in their orbital planes. And now they all point up. It's hard to do this with my hands. And now their noses point up. Eventually, there's differential precession. So orbits at different semi-major axes are going to precess at slightly different rates. And so eventually, that will actually drop down. We don't see that completely going in our simulations. The differential epsilon precession rate is clearly not fast enough for us to see that. But you will see that going to zero in some other simulations where you have more rapid precession. The omega clustering, we think what's happening here, the pomega, sorry, that this physical clustering in space, we think what's happening is that we have so few particles in our simulations that the bodies are moving on these torques and they're aligning, but then you're having really strong gravitational scattering encounters between bodies on these overlapping orbits, and it's tossing them aside and changing the torques that they're feeling because they're being thrown outwards. And that's why the plot on the next slide was so important, just showing as you decrease the individual masses of these bodies, those scattering encounters get less and less strong, and they shouldn't be this strong, it's artificially high, and you get stronger and stronger clustering. With the eccentricity and the inclination, the Kepler elements, these are mean values, and so once you've undergone the inclination, the orbits stay with a mean high inclination value, but they still experience into-orbit torics, so you get these oscillations. And with that eccentricity, it's really interesting because you can see particles actually go to radial orbits again, and back down to circular orbits and radial, and when they're on very eccentric orbits, they're actually going to be coming back inside the solar system as maybe Halley-type comets, or at least a source. Did that answer the question?
That was
yeah.
from Eddie Nerney. I've got a couple more questions in the chat for you. Should I go ahead?
Will I take one more? I'll take one more from the audience because they're here and it feels nice. And then we'll go back to the chat. Yeah.
Thank you for nice talk. And my question is, you assumed the massive scattered disk as the initial condition, but the formation timescale of the massive scattered disk is short enough to be assumed as an initial condition? In other words, can you start from the formation of the scattered disk?
So I think your question is like the timescale for the formation of the scattered disk, and like, can this happen fast enough?
Yeah.
Yeah. So Alex is actually here and he's nodding, right? So what we would want to compare is the E-folding timescale of this instability, because once the orbits start inclining, they start detaching, and so they stop scattering. So the E-folding timescale compared to the timescale for energy diffusion out of the solar system. Alex, you're nodding. Do you have numbers on that, or?
Yeah. So we'll go like a 20-year mass disk, and like with the downtime and everything, the E-folding timescale is like about 15 years, and the scattered disk. There's a lot going on in the solar system around this time. Like Neptune is probably migrated, creating the scattered disk. The time period for this is similar, like tens of millions of years. So the timescales are comparable.
And the really other for this feature.
So at some point, Neptune is going to like deplete the scattered disk. So as it's like actively scattering scattered disk, so you can't lose too much mass. So you want them to be kind of the same. Otherwise, if they weren't the same, the disk might get depleted before you're not building. But because they are similar.
So for those in Zoom, we're concluding that the timescales for the generation of this scattered disk, but before the scattered disk particles make it out to the Oort cloud, and the E-folding timescale are of the same order, like 10 million years, depending on the mass of the disk, right? So we need that massive disk to decrease that E-folding timescale.
Got another question from Nick Schneider. Are there any constraints on your new population of objects? A few large ones or a zillion tiny, undetectable ones? Do their orbital properties need to be maintained by yet another population?
So the question is, are there any constraints on the size distribution of these bodies? And the second one is like, do we need another population of bodies or another body to maintain the configuration or the alignment? So the answer to the second one, no. Nope. You do all collective gravity from these minor planets themselves. We don't need anything else to actually maintain the structure. And then to answer the first, I mean, right now we have no constraints on the bodies that we actually see, because Sedna, for example, doesn't have a moon. We just don't know what mass the object is. But I think we should assume that they are very similar to the Kuiper belt object distributions. just because these bodies should have formed closer in towards the sun and been scattered outwards. So we should look to the planetesimal populations we can actually observe and use that as a basis. And we'll be doing that with LSST.
I have a quick observational question. You mentioned the Vera Rubin telescope. My question is, are there any other telescopes that would, in the future, in the near future, would help resolve this mystery? In particular, JWST. Would that be helpful?
Right now, there are individual surveys like AUSOS, kind of already using telescopes around the world. But other than Vera Rubin, I'm not sure. Does anybody know about JWST? The question was, are there any other telescopes we're waiting for? I'm seeing shakes, just of like, Vera Rubin or bust. Yeah. One thing that is great is there are campaigns now with the Subaru telescope to look for Planet 9. These are ongoing campaigns looking at archival data. So that's actually thrown up more objects, just that search for Planet 9 itself. And so that's been really helpful. But yeah, Vera Rubin, I think, is what we're going to